Assalamu alaikum. Welcome to today's session. So up to the last class, actually, we discussed mainly about the generation side. Basically, we talked about the dynamic modeling of the synchronous machine, that is the conventional generation system. And then we continued the discussion from the generation end, actually. We talked about the dynamic modeling of the exciter, okay, that will actually control the reactive power out of the generation system. Then we also talked about the design of the power system stabilizer that would actually help us in enhancing the system stability, of course, the small disturbance stability. And in between, we talked about the linearization process. And that was done actually with the help of the Taylor series expansion and some higher order terms. We terminated or we neglected some of the higher order terms so that the resulting system becomes linear. And then we continued the discussion on the generation side. Basically, we talked about the dynamics of the turbine, that is the hydro turbine system. And then we also talked about the dynamics of the governor system that would ultimately control the fuel input to the turbine system. So that was done up to the last class. So today what we will do, we will continue our modeling part, but now we will be more focused on the load end, okay? So basically, if we consider the load scenario for a power system, we can distinguish different kinds of loads based on their characteristics. For example, in most of the cases, in most of the industrial loads, as we all know, are induction machine. That means most of the cases, these are dynamic loads. However, in our residential system, besides the dynamic loads, we also have some static loads. So when we talk about the static loads, there could be, the loads could be varying in nature. However, if we talk about the dynamic loads, that's the industrial loads, we can mostly focus on the induction machine. And more specifically, that would be three-phase induction machine. So basically, while we consider the dynamic modeling of the load sides, we in our this course will be mainly focusing on the dynamic modeling of the three-phase induction machine. However, in case of the static loads, generally what we can get, they call it like ZIP model, where Z stands for impedance, I stands for current, and P stands for real power. In short, we call them like constant load model. So we call it like constant impedance, constant current, or constant power loads. So basically, the static models could be either treated as any of these three types. But because we are mostly interested in the dynamic stability or the small disturbance stability of the system, so our main focus in this course would be to continue our discussion on the three-phase induction machine. However, if you are interested in the discussion of the static load model, you can take help of any standard advanced power system book. Okay, if I get some time, inshallah, I will try to have a little overview on this, okay, modeling. However, in today's class, I will start with this three-phase induction machine model. So if we look into the constructional part of the induction machine, and if I want to compare the constructional part for the induction machine with respect to the synchronous machine that we have already discussed throughout our lectures till now. So basically the machine construction could be divided into two main parts. One is the stator part, the part of the machine which remains stationary throughout its operation. And another one is the rotor part. With respect to the stator construction, because we are focusing on the three-phase type induction machine, So the stator construction for the induction machine and the synchronous machine are exactly same. So that means in the stator of the synchronous machine, we had balanced three-phase coils. Similarly, in the stator of the induction machine, the same configuration would be available. So from the stator point of view, they have identical construction. No difference at all. So like the synchronous machine, as we said, in case of the synchronous machine, the machine could be used either as a generator or as a motor. The same conclusion applies, or the same principle applies for the three-phase induction machine. So similarly, for the three-phase induction machine, we can also say that, well, we can either use it as a three-phase induction motor as a load, or if we reverse the connection of power flow, or if we want to reverse the direction of power flow from the conversion of power flow, then we would get the generator with respect to the three-phase induction machine construction. So the same machine could be used either as a generator or as a motor, like the synchronous machine, with a little change in direction of energy flow or power flow through the machine. However, if I look into the rotor part construction, then there is a significant difference. In the synchronous machine, the rotor part, we mainly talked about salient pole and non-salient pole, and we had a detailed discussion on this. However, in case of the induction machine, can anyone tell what are the basic configurations for the rotor part in induction machine? Three-phase induction machine. How can we differentiate the construction of three-phase induction machine? There are basically two types. What are the types?
Squirrel cage.
Squirrel cage, excellent. And
own rotor type.
Own rotor type, excellent. So these are the two main types. Okay. So the basic difference in the rotor construction again lies in the fact that in case of a squirrel cage, basically there are no physical coils over there, okay? Like the no physical wirings are available in case of the squirrel cage. Rather, you have the rotor copper bars or the conductor bars, okay, metal bars or conductor bars, which are actually shorted at both ends in case if it is a squirrel cage construction. However, for the wound rotor case, we have three-phase coil. Three-phase coil configuration. So if it is an own rotor machine, in that case, the stator carries three-phase coil and the rotor also carries three-phase coil. However, if it is a squirrel cage type, then the stator only carries the three-phase coil, A, B, and C, but the rotor doesn't carry the three-phase coil configuration. Rather, the construction is something you can say like this. There are rotor bars, and these are the two ends. These are the rotor slots, cross-sectional view, you can say. And both ends are actually shorted at like this. So there are rotor bars or rotor slots. Simply short them out at both ends so that you have you get a path for the induced voltage to produce the current through the conductors, and ultimately that would produce the torque, okay, required torque on the rotor body, and that would ultimately provide you the rotation if it is a motor operation. So but in case of wound rotor case, in case of wound rotor, what you have basically, if this is the stator side, three-phase coil. Okay, so you have the rotor side three-phase coil like this, and ultimately you have a provision actually to connect these to a block of resistors, three-phase resistor block like this, which will ultimately provide you some level of control. Okay, so this block actually provides you some level of control over the torque that is produced on the rotor. However, if you do not want to have this control available, then simply you can short them. But ultimately, what you have to do to run the machine, you have to make sure that this path is closed. This path is closed actually, like this. Otherwise, you don't get any closed path for the current to flow, and ultimately the rotor won't run. The rotor won't rotate, even if you give a three-phase supply over here. Okay, considering you are supplying three-phase power. So even if, so that means if you're not shorting this out, then the path is not closed, and ultimately you don't get any current. I rotor becomes 0 in that case, and you don't get any torque out of the own rotor machine. Okay, so these are the very basic things. Just I gave a small review on that, just to have you recap on the constructional differences between the synchronous machine and the own rotor machine, three-phase types, both cases. So that means in the modeling part, we have a little bit of differences. So before we go into the model, let's look at some other important points where there is some differences between the synchronous machine and the induction machine. So let's start from the stator side. They are exactly same. Okay, as I said earlier, that from this stator construction point of view, the synchronous machine and the wound and the induction machine, three-phase type, are exactly same. So in both cases, they carry three-phase coils, phase A, phase B, and phase C. And this is also, I mentioned just a few moments back, that you can have either wound rotor type or the squirrel cage type for the rotor construction. And if it is wound rotor type, so in that case, the rotor also contains the three-phase windings, phase A, phase B, and phase C. And the rotor coils are such that whenever there is the magnets are actually induced on the rotor body or the rotor coils, they behave in such a manner, they are wound in such a manner that the number of rotor poles are exactly the same as the number of stator poles. So that is actually done by the manufacturer at the manufacturer end. Now, in this case, as we applied the DQ0 transformation, that is the Parks transformation in case of the synchronous machine. So in the similar manner, we could also go for the DQ0 transformation. And by now, we all should know what's the benefit of the DQ0 transformation. So from the ABC frame, the benefit of the DQ0 transformation should be known to all by now. There is another very specific difference between the construction of the synchronous machine and the induction machine, and that is, in the synchronous machine, throughout our discussion, we considered that we have a salient pole construction. Okay, so if I again give a little recap of that. So this was the, let's say, the stator part, the cross-section part, of course. So we said we have three-phase coils, phase A, phase B, and phase C. And at the middle, we considered the cross-section of the rotor like this. So let's say if it is a two-pole machine, then what we did, we actually introduced this field coil, which was actually supplied by some external DC source. So this was the construction of the salient pole synchronous machine. Salient pole synchronous machine. So as we saw there, you can clearly see that if we talk about the axis, that is the D axis, we considered along this path, along the main field, and 90° out of it was the Q axis. So you can clearly see that the air gap path that is being traversed by the magnetic field along the D axis and along the Q axis are actually clearly different. Okay, you see the air gap here. Along the Q axis, it is quite large. However, along the D axis, it is pretty small. So this air gap along the D axis and this air gap along the Q axis are different. So this was the conclusion. However, in case of the induction machine, this is the conclusion. You have a cylindrical rotor, okay, cylindrical rotor or non-salient rotor. And what that gives actually, that gives us this thing, uniformity in the air gap. And this uniformity means basically you have AGD is exactly equal to AGQ. Okay, so that point would be clearer once I introduce the diagram, the schematic diagram for the induction machine under consideration for this lecture. So for the cylindrical rotor, what we will get is this uniformity in the air gap, and this air gap actually means this along the D axis and along the Q axis, because we are considering cylindrical type or non-salient pole type configuration. And accordingly, because of this relationship, we can conclude this one. So there's no difference that you can get between the d-axis inductance time constants as well as and the q-axis inductance and time constants. So if you remember, in case of the synchronous machine, we talked about td dash. We didn't talk about tqo dash because we simplified the model before that. So we didn't introduce actually this, but because of this, actually you would get tqo dash for larger larger order model for the synchronous machine. Okay, you would get this. However, in this case, because we have uniform air gap, you get identical inductance along the d axis and q axis because of exactly equal air gap, and identical time constant. So we won't use actually td dash and tq dash in this case. Rather, so td dash and tq dash you will not see here. Rather, probably you will see something like this, to dash, open circuit time constant. So in other words, you can also say, well, if you want to use this, then you can use like this. So tdo dash is equal to tqo dash would be equal to to dash, a single time constant along both axes. Okay, so these are some of the striking features that we should know at the start of our modeling. There are a few more points that I would like to mention in the next slide. So let's go there. So this is very important, very, very important slide, okay, for the understanding of the next part of the lecture. So please want to have your careful listening for this specific slide. Okay, so let's start. So for the synchronous machine, what we did, if you can recall clearly, what we did was we aligned, or we assumed that the d-axis was exactly aligned with the rotor of the machine. So that means what? That means in case of synchronous machine, let me draw the diagram again. So this was the stator coils A, B, and C, and this was the rotor construction. And along this line, along the rotor body, what we did actually, along the center of this axis, we considered that this was our d-axis. Okay? This was our d-axis. Okay. And what we also assumed that whenever the rotor would rotate at steady state, this speed, the speed of the d-axis, what we assumed was the synchronous speed at steady state, remember. And now 90 degree out of phase, either in this direction or in that direction, we assumed the q-axis. So in a steady state, what we assumed that the rotor body, of course, the rotor would rotate at synchronous speed. So this is omega synchronous. So because the d-axis was assumed to be aligned along the rotor axis, so of course the d-axis was also rotating at omega synchronous. This was in case of synchronous machine. Okay, so this is a recap, and this is what is mentioned. So the d-axis was also rotating at, so d-axis was rotating at synchronous speed. The rotor was also rotating at synchronous speed. But as we all know, for the induction machine, the rotor does not move at a synchronous speed. It never moves at the synchronous speed. So the rotor speed for the induction machine is never equal to the synchronous speed. For the motor operation, omega r is always less than omega s. For the generator operation, omega r is always greater than omega s. So in short, we can say that omega r is never equal to omega synchronous, even in steady state. That is the important thing. Even in steady state, this is true. So this is point number 2. Now, if we consider that we have the wound rotor configuration, that means we are talking about the presence of the physical coils, 3-phase coils within the induction machine. So that means the stator has 3-phase coils. The rotor also has 3-phase coils. Now let's go back to the basic of the induction machine operation. The basic of induction machine operation. Let's see how many of you can remember it clearly. Okay. So how does the induction machine starts rotating? Anyone? So this is, I'm talking about induction motor, remember, not the generator. Again, this is 3-phase coil. Because it is a motor, so what we would do, okay, let me draw some rotor coils also. These are the rotor coils, let's say. Let me make it like look like 3-phase coils, not more than that, just to make life easy. So these are rotor 3-phase coils, let's say. Okay. So how would you start the induction machine? Anyone?
First, right, supply the 3-phase power.
Supply 3-phase, excellent.
So that will create a rotating magnetic field because of the phase angle variances. And this rotor, with respect to this rotating magnetic field, the stator bars are initially stationary.
Not the stator, rotor.
So rotor bars,
yes.
The rotor bar are initially stationary, so there will be a current flow in the rotor bars. And due to the current flow, the rotor bar will have its own magnetic field.
Excellent.
This magnetic field will as we know from Lenz's law, the creation of any electromagnetic force tries to oppose its creation. So this magnetic field will the rotor will try to move in such a way that this variance in this current flow is stopped. To do that, the rotor has to rotate synchronously with the applied rotating magnetic field. When the rotor tries to move in that way, it reaches at a certain speed. At that speed, the speed of the rotating magnetic field and the rotor is essentially the same. Then there is no magnetic flux cutting, and the rotor slacks behind because there is no current flow. And then again, there is some speed.
Okay, I will take the first half part of your explanation. The next half part probably you just mixed it with the operation of the synchronous machine. Okay, so the first half is okay. So would you mute yourself, please? Okay, thank you. The first half is okay. So let me again continue from where he started. The first half was okay. So what would happen? Basically, we provide a 3-phase current, okay, or 3-phase voltage, whatever 3-phase supply is given. Due to this 3-phase balanced supply, remember 3-phase balanced supply is given to a 3-phase balanced set of winding in the stator. So there are 2 conditions: 3-phase balanced supply, 3-phase balanced coil. Means 120-degree electrically apart. They are wound in such a manner that they are 120-degree electrically apart from each other. So each phase, from each phase to another phase, next phase, there is 120 electrical degree difference in phase. Magnitude remaining same because it is a balanced system. So what would happen, as he said, we will have a rotating magnetic field, RMF. So this RMF speed is synchronous. So the rotor stator coils are stationary. Remember, stator coils are stationary, but the coils, once they get these three-phase set of current, they would return you a magnetic field which is rotational in nature. That means its magnitude is peaking, reaching its peak at different instants. At different instants, it is peaking at different position. So in short, we call it rotating magnetic field. So as a viewer from outside, it would seem like it is rotating or it is changing its position with respect to time. Or in other words, in short, it is rotating, okay, like this. Actually, the resultant magnetic field would be rotating in nature. The basic mathematics is covered in your undergrad level. So once it happens, now remember the rotor here was stationary at the very beginning. So what the rotor coils would see, it would see that, well, there is a changing magnetic field with respect to time. Okay, it would see that, well, there's a magnetic field sweeping over its surface. And accordingly, based on the Lenz's law, the rotor would try to catch up. The rotor would start to rotate in such a direction that would reduce the induced effect. Okay, so once this omega, because of this omega synchronous, this omega at the very starting point, this omega r is 0. So what's the difference between this RMF? This is RMF. This is your rotating magnetic field or omega synchronous. So at the very beginning, the difference, the relative speed, we call it the relative speed between the rotating magnetic field and the rotor itself is maximum. Omega synchronous minus omega r is 0. So the difference is omega synchronous at the very beginning when the rotor is stationary. So because of this relative speed, the rotor coils would get some induced voltage, maximum induced voltage. And as I said just a few slides ago, that the rotor coils should be short circuited. In the squirrel cage, from the manufacturer end, it is actually short circuited. But if it is an own rotor, as a user, from the user end, you have to short it, either through the help of the resistor, okay, simple resistors, or you can also short it directly, but you have to short it. So once those coils are shorted, you will find that there is a closed path for that induced voltage to flow through the rotor coils. And accordingly, because of that rotor current flow, the rotor would start to get a force, okay, motor action, force on the conductors or on the coils. And due to the Lenz's law, the force direction would be such that this relative speed value gets reduced. So if the RMF direction is in this direction, at the starting point with the application of these three-phase supply, the rotor would start to rotate in the same direction, However, the rotor would never be able to catch up with the RMF, because in that case, there would be no induced effect, okay? There would be no induced effect. So this is in the last part, actually, the explanation from your end was a little incorrect, but the remaining part was okay. Okay. So the rotor would never be able to catch up with the RMF, never be able to catch up with the RMF because it is a motor action. So always your omega r would be less than omega synchronous. It will always lag behind. And this difference in speed is basically known as the slip speed. Okay, this difference in speed is known as the slip speed. And the amount of current that would flow through the rotor coils, is a function of slip. That I'm coming next. Okay, so this is basically the operation. So what it means, you remember throughout the discussion, I said that the rotor coil would get a three-phase induced current because there is a three-phase coil. So the rotor coil will carry its own current. And once it carries its own current, those rotor coils would give you back its own rotating field. its own rotating field. Remember, its own rotating field. Okay, its own field. So you have a stator field or a stator magnetic BS, magnetic field density, magnetic flux density, and rotor magnetic flux density. So you have BS and BR. So the induced torque could also be produced as a function of BS, interaction between BS and BR. That is another way to express the torque generated on the rotor body for the induction machine. So in short, once you get the current flowing through the rotor coils, it would produce its own magnetic field that is termed as BR. And the second observation, that these speed, rotating magnetic field speed and the rotary speed would never be same. There would be always some slipping behind, some difference in speed that is known as the slip speed. So now there is the difference that starts, and there's a very important point where there is difference between the induction machine and synchronous machine. In the synchronous machine, what we did, we assumed that, again, I'm going back to this point, the first point. So in case of the induction machine, what we did, we said that the D axis is aligned with the rotor. D axis is aligned with the rotor. Why? Because the rotor itself was rotating at synchronous speed, at least in a steady state. Of course, in the dynamic state, it would vary. But in any other cases, in any steady state operating point, the rotor speed would be the same as the synchronous speed. This is for the synchronous machine. For the induction machine, this is never true. Even in the steady state, the rotor would never rotate at synchronous speed, be it a motor or the generator. So we can't actually assume the same way, we can't assume the same kind of D-axis alignment for the induction machine as we did for the synchronous machine. So there's a problem. So what we have got an RMF. Let me write again. We have got an RMF, rotating magnetic field, in the stator circuit, or due to the supply in the stator circuit. The RMF is rotating at synchronous speed. The rotor is never rotating at synchronous speed. Rotor is running at some, so this is rotor. Rotor is running at some different speed other than synchronous. So what we would do, and what about the stator coils? Stationary. Remember, the stator coils itself are stationary. They have zero speed. So omega stator, speed of the stator coil is actually zero. This part is exactly same as the synchronous machine. This part is exactly same as the synchronous machine. However, this part is different. This part is different. So what we would do now, we would assume now that we have a DQ axis configuration. We have a DQ axis configuration which is running at synchronous speed. Remember, which is running at synchronous speed, but that is neither fixed to rotor nor fixed to the stator. We can't fix it in any place. Why? Because in case of induction machine and in case of synchronous machine also, the stator is stationary, right? Stator is stationary. Its speed is zero. If you want to represent it with respect to speed, with the help of speed, its speed is zero. There's no speed. Synchronous machine, we had a benefit that the rotor rotates at synchronous speed. So we had an additional advantage. So what we did, we assumed that, well, the D-axis is also aligned along that axis. The D-axis is also rotating at synchronous speed. So we assume the D-axis along the rotor axis. That was the benefit that we got in case of synchronous machine. In case of induction machine, unfortunately, the rotor is not running at synchronous speed. So what we can do, the only way we can assume the D-axis, sorry, the DQ axis, is to have a new set of axes D and Q, which is running at synchronous speed, but we cannot set it to the stator because the stator is stationary. We cannot set it to the rotor because rotor is not running at synchronous speed. It is running at omega r. So we have no other way but to choose a different set of axis, which is running at synchronous speed. So that means I will, everything I think will be clear in the next diagram, what I am saying. Okay, once you see the diagram, I think this, whatever I am saying would be much more clearer. So what I'm saying was the difference. In case of induction machine, we have to assume a different set of DQ axis, which is actually not aligned to the rotor, like the synchronous machine. In synchronous machine, in a steady state, rotor was moving at synchronous speed. So we could assume that the D axis is also aligned along the rotor axis. Induction machine, the rotor is running at non-synchronous speed or asynchronous speed. So if we want to introduce the DQ axis, which is rotating at synchronous speed, we have to, of course, introduce a new set of axis. Okay, we can't align it along the rotor, neither align it along the rotor nor align it along the stator. So that is the conclusion. And what would be the benefit now? If we can bring this new axis into the picture, new set of axis, DQ axis, which is running at synchronous speed, what we can do then, stator coils or stator quantities are stationary. We can bring them to the DQ axis. We can transform them into DQ axis quantities. Rotor quantities, which are running at non-synchronous or asynchronous speed, we can also bring them to the, we can map them to the DQ axis. So this is the benefit. DQ axis is moving at synchronous speed. So what you would do, we would bring everything to the DQ axis, the rotor quantities, the stator quantities, the rotor flux linkage, the stator flux linkage, the rotor voltages, the stator voltages, rotor current, everything. We will bring it to the synchronously rotating DQ axis. Okay. So this is what is meant over here. The next point is, I just mentioned earlier, the current in the rotor coil. Okay. What is happening with the current in the rotor coil for synchronous machine? It is basically supplied from an external source, external DC source. So for a synchronous machine, the rotor current is actually controlled from an external source, DC source. However, for induction machine, there is no such excitation. The rotor current is purely based on the slip speed. So the rotor current in case of induction machine is not a function of some external voltage source, not any external voltage source. Rather, it is based on the slip speed, the difference in speed between omega r and the RMF. That is the omega synchronous. And the last point here is, I have also already mentioned it, that the same model you could use for the motor model and for the generator model. The only difference lies in this omega synchronous minus omega r. This is your S. For the motor, this is positive. For the generator, the slip is negative. Because in that case, omega r becomes greater than omega synchronous. That is for the generator case. Okay, any question up to now? Because slowly now we'll be going into the mathematical part. No question, that's good.
Is this true for only three-phase machine?
Yeah, I'm talking about three-phase machine. Single-phase machine has a completely different scenario. Okay, you have to introduce the capacitance, or you have to somehow split the phases. Okay, otherwise you have pulsating torque. That is different thing. I'm talking about three-phase machine, remember, not single-phase machine. Everything that I'm talking about in this lecture are solely related to three-phase induction machine. Okay, so now let's start with the schematics of the three-phase induction machine. So like the synchronous machine, we have some similar kind of notation. So again, the direct axis is the D axis, the quadrature axis is the Q axis, the dot means the current is coming out of the page, the cross means the current is going into the page. Now there are slight differences. The difference starts from here actually. So ABC, again, these are stator quantities because we have three phase. So the small ABC, these are the representatives of the stator quantities. The capital ABC, however, are used for representing the rotor quantities. Again, rotor three phase, I'm talking about one rotor configuration. So we are talking about physical coils, three phase coils. So again, capital A, B, and C, these are related to the rotor quantities. Okay, so let's see the coils now. So let's start with the stator. So remember, I'm talking about induction motor actually. So you have to be very careful about the current direction between the motor convention and the generator convention. Now I'm talking about motor convention. So the current direction should be into the coil. Okay, into the coil. So this is coil A for a stator, A dash. So the current is coming out of the page because this is the dot coming out of the page, and this is going into the page. So if you apply your right hand thumb rule, your magnetic flux axis would be along this line. So this is your magnetic A axis for stator A coil. Okay. And this is actually the physical coil where you were drawing the physical coil. Okay. The current is entering, the phase A current is entering into the coil, A axis coil. And this is the applied voltage per phase, that is phase A voltage, VA. So similar kind of thing you will get for phase B here. That is 120-degree lagging, phase B from phase A, small b. Remember, small b, small a, these are stator coils. So again, this direction of B axis, small b axis, you can obtain from this B dash. So this is out of the page, this is into the page. So again, if we apply the right hand thumb rule, your B axis, stator coil, stator magnetic field B axis would be along this line. And this is the corresponding physical coil. IB, current is getting into the coil. This is the applied voltage VB, small v, small b. Now the third one is C, and in the same manner, you can get small c and small c dash. So this is out of the page for coil C. This is into the page for coil C. Again, if you apply the right hand thumb rule, you will get somewhere here around approximately. So this is C axis. This is missing actually. You will get I small c. Again, current is entering into the coil, and this is the applied voltage VC. Okay, so this is all about the stator. Now come to the rotor. The rotors are actually drawn with red colors just to distinguish with the help of color coding. So let's start with the rotor. Now, this capital A axis is this is your A axis for the rotor. How do you get it? Again, this is A for the rotor, capital A for rotor, capital A dash for rotor. Again, this is out of the page, this is into the page. So again, if you apply the right hand thumb rule, your A axis would be somewhere here. This is for rotor, capital A. V, capital A is the voltage that is induced actually. So VA is not the applied voltage, remember, it is the induced voltage. However, V small a, it is the applied voltage. So there is a difference between VA and this VA. This is externally applied voltage. This is induced voltage. And due to that induced voltage, you are getting some induced current in the phase A coil I, capital A. Okay. Okay. So similarly, you get the similar kind of conclusion for BB dash. So that would be along this line. Again, this is I capital B, V capital B. These are induced effects. Similarly, you get C dash along this line. Again, this is I capital C, V capital C. Again, these are induced effects. Okay, so this is all about the coils for phase A, B, C for both stator and the rotor. So this part is done. Any question? Very simple, nothing special. Okay, so let's continue. Now what's next? Next is the speed of the corresponding axis. So the speed of the stator axis, of course, these A axis, B axis, small a, small b, and small c axis, they would be fixed along these lines. Okay. Of course, they will change their direction, but either they will be along this line. I mean, if we are considering exactly at this stand of current direction, because these are three sets of AC current, alternating applied voltage. So at certain stand, this A at this end, it is out of the page, this is into the page, but after 180 degree, they would reverse their direction. Okay, they would reverse their direction. So in that case, the A axis would be along this line. So either your A axis would be along this line or along this. So this is basically the A axis, you can say. This big axis is the A axis. So either it will go in this direction or it will go in this direction. So the B axis for the stator, either it will go along this direction or it will go along this direction. C axis like this. Okay, so this is the C axis. But the coils itself, they are not moving at all. The coils itself, the physical coils, they are not moving at all. However, the rotor coils, they are moving because the rotor itself is moving. So the rotor coil setup is moving at a speed omega r, at a speed omega r. So that's why you see in the rotor coils, along the rotor coils, there is omega r speed. Okay. This speed is 0. This omega is 0. Omega stator is 0. Omega r is non-zero. It is the rotor speed. But again, this omega r is never equal to synchronous speed. This omega is 0. So now, how do we introduce the dq axis, which is moving at synchronous speed? Because the rotor is not moving at synchronous speed. Stator is fixed at 0 speed. So if you want to introduce the dq axis, which is moving at synchronous speed, we have to introduce a new set of axes, that is d and q axis. We can't align this dq axis along the rotor, okay? Because the rotor is not moving at synchronous speed. This is why we introduced a new set of axes, that is dq set, which is moving at omega s, which is actually same as omega synchronous. So this is the reason of introducing a new set of axes. I hope it is clearer now after this diagram is being discussed. So this is our dq axis now, which is moving at synchronous speed. So again, this is moving at synchronous speed, this setup, d and q. Omega r, it is the speed of the rotor coils or the rotor setup. And omega r is always less than omega s because we are considering it is the motor operation. So there will be a lag, phase lag between the d axis and this rotor axis. And we consider that phase lag to be theta r, theta small r. Okay. And because a axis is fixed, but this rotor axis, rotor a axis is moving with respect to time. It will move at a speed omega r. So there will be also some phase difference between this stator a axis and the rotor a axis. And we denote it by the theta. So there are two theta. One is the phase difference between the stator a axis and the rotor a axis, that is theta alone. And there is another theta, which is the phase difference between the rotor and the d axis, that is theta r. So this is the explanation of theta and theta r. Any question? From now on, we will be moving directly into the math. So the diagram things are done. Diagram related things are almost done. So if this is clear to everyone, then
Yes, sir.
yes, okay, thank you. So let's start with the mathematical process derivation. So now, how do you relate theta and omega r? Again, go to the diagram. Remember, theta is this angle. So let's say when time equals to 0, this a axis was exactly aligned along the a axis. This is an assumption. So if that is true, as time t will go on and increase, we can easily relate this theta and this omega r by this relation, isn't it? Theta equals to omega r into t. When t equals to 0, theta is equals to 0. When t is non-zero, this is the relationship, okay, between this axis, and the angle is actually represented simply with the help of this speed, omega r. Next, what is sleep? This is actually, you have got the idea of the sleep from your undergrad level. The sleep is simply omega s minus omega r divided by omega s. So sleep speed is omega s minus omega r. This is sleep speed. But the symbol sleep alone is once you divide the sleep speed by the synchronous speed itself. So that is sleep. If you want it in percentage, simply multiply it by 100. So that would give you the percentage sleep. But in general, sleep is this: omega s minus omega r. Omega s is the speed, the synchronous speed. Omega r is the rotor actual speed. Omega s is again the synchronous speed. So let's move on. Okay, so the first two are actually repeated from the previous slide. So what's next? Let's see what's next. So in the next one, we try to relate theta and s. So how to do it? The simple mathematics. So you see, theta is equals to omega rt. So if we continue with this, we get s omega s equals omega s minus omega r. So omega r equals omega s minus s omega s. You take s, sorry, can't take s. You have to take omega s 1 minus s. So this is omega r equals to omega s into 1 minus s. So theta r is omega rt, and we replace omega r by this omega s into 1 minus s. So you have 1 minus s omega s into t. So that's it. Next, you have, again, we try to relate theta r with omega s. So what is theta r? How do you get theta r? And this relation, the first relation, how do you get it? Anyone? This is actually the same concept as we used for establishing the relationship between the delta for the synchronous machine and the theta m for synchronous machine. So actually the same thing that we are doing for these two thetas here. So again, we go to the diagram for understanding this specific relationship. So theta r is omega st minus omega, okay? So this is actually theta r. What is this? This is theta r plus theta, right? So theta r plus theta. Now, what can we write in terms of omega s? So this whole distance, can we write it like omega s into t? Means when t is 0, this d-axis is aligned, is assumed to be aligned along the a-axis. This is what it means. As t increases, you will get theta and theta r, both will be there. Okay, so this is the relationship. Theta r plus theta is omega s into t, and then theta r is simply omega st minus theta. And once you get it, you replace theta from here. So omega st minus 1 minus s omega st. You simplify this, omega st minus omega st plus s omega st. So these two cancels out. So simply you get s omega s into t. So this is what you have here. Okay. Next, if we want to have the dynamic set of model for this theta r, so what we do, simply you take the time derivative. So we are actually looking for the time-based dynamics, okay, dynamics of theta r with respect to time variable. So simply you take the first time derivative on the left-hand side, and you do the same on the right-hand side. So t would be cancelled. Simply you will get d theta r over dt is simply s into omega s. And if you use this relationship, you can also continue a little bit further by replacing this with this, right? So d theta r by dt can be calculated from this. that is S omega S would be the result. And if you replace S omega S from here, S omega S, you multiply it and bring it to the other side, you simply have omega S minus omega R. So either you can write d theta over dt is omega S minus omega R, or you can also write S omega S. Okay. Okay. So let's move on. So if this part is done, now, so this is equation number 1. That actually forms the first set of dynamic equation for the induction machine model. For the 3-phase induction machine, this is the first set of dynamic equation. First dynamic equation. D theta R over dt is S omega S, and that is also equal to omega S minus omega R. So either you can model your system in terms of slip, or you can also model your system in terms of omega R. So if you want to keep omega R as your state variable, then you use this expression. On the other hand, if you want to use slip S, if you want to keep it as your state variable, then you use this one. All the same. Depends on your choice. Depends on your choice. Which one is preferred by you? Either one is okay. Okay, so now the next few slides are pretty simple because they are exactly or almost identical to the synchronous machine model. Because now we will be moving into the stator winding voltage expression. We have 3 sets of coils, VA, VB, and VC. So it looks almost similar to the synchronous machine model, except a little difference. Can anyone say what's the difference?
The signs.
For which one?
RSIA.
Sorry?
RSIA, RSIP, RSIC, this should be minus.
Yeah,
this was minus.
there was a minus. There was a minus because it was generator. Okay, so the current was coming out of the machine. Current was coming out of the machine. So we assume that the current into the machine is positive. The current out of the machine is negative because this is motor. So if we go back to this diagram now, you can find out the difference quite easily. So in case of generator, synchronous machine model, these IB, this IA, and this IC was actually in the reverse direction. They were coming out of the system. But in this case, they are going into the system. Okay, so that's why there is a little difference. And that lies actually solely in this part. Minus RSIA, minus RSIB, minus RSIC was there for the synchronous generator model because this is induction motor. So in the stator coil winding voltage expression, KVL, you simply replace that minus with plus IA. And this RS is the stator coil resistance for, and because there is a balanced set of winding is being assumed. So you have RSA equals to RSB equals to RSC. And in general, we write it RS. So simply you are applying voltage VA, VB, VC. Some part is there dropped as the resistive drop due to the current flow, and the remaining part is the flux linkage in the 3 set of coils. So this is the stator winding voltage. Similarly, we will get the rotor winding voltage. Just be careful about the notation here. This is small, all are small a, small b, because small a, b, c are associated with this stator. Now next would be, we will get the rotor winding voltage. Similar kind of expression, simply the lettering fonts are different. Those, the previous one were small letters. Now you have capital letters. Again, the rotor is getting induced current and induced voltage. Okay. So VA equals to RR, IA now, RR, all these RRs are simply the rotor resistance, and the remaining part are the flux linkages. We are always using the capital letters for rotor quantities. Now, can anyone say the difference between the stator VABC over here, the stator ABC, and the rotor ABC? Any difference?
Capital A.
Hey, no, other than that, numeric value. Remember VABC for the stator, these are applied voltage, okay? Physical voltage, applied real life voltage, okay? But in the rotor circuit, are we applying any external voltage? VA, VB, and VC?
So induced voltage, so it will be
Yes,
less than the stator voltage. I
less
mean,
than.
the copper loss will be the errors.
Okay, so this is one answer. Anyone else? Let's go to the rotor coils again. Let's go to the rotor coils. If it is wound rotor, you'll get something like this, right? Let's say this is the rotor, three-phase rotor coils. Phase A, phase B, and phase C. Now, VA, VB, and VC. These are the induced voltage on these coils, right? But to have this current flow, IA, IB, and IC, what you have to do? What you have to do with these three ends? Short them. So if you short them, what is the voltage here in this shorted path? Zero. So these would be zero. You get the idea? So all these would be zero. However, for the stator part, you are applying external three-phase voltage. This can't be zero. VA, V small a, V small b, and V small c, they are never zero, because this is the externally applied you are externally applying your input energy, electrical energy. But the rotor coils, either they are shorted from the manufacturer end, okay, for the squirrel cage, or you have to close the path through the resistors, or even without the resistors, you have to close the path. Once you are closing the path, there is no resistive element. There is no resistive element. So there is no way there would be any non-zero voltage available, okay? So the voltage drop would be actually zero. These VA, VB, and VC, these are actually, you can say in one way, these are the voltage drops along this path. Voltage drops or rise, whatever you say, following the KVL, whichever is applicable, either voltage drop or voltage rise. But because these are short circuited, along the short circuited path, you don't get any voltage drop or voltage rise. So numerically, these values would be ultimately zero. We will see it later on, okay, where we are actually reflecting this thing in the modeling part. For the time being, we are simply keeping them as VA, B, and C, capital, all caps. But I'm just mentioning it here so that later on, when time comes, I don't have to repeat it. Okay. Now, let's see the stator winding flux linkage as we saw for the synchronous machine case. Similarly, we will see something here that is also known as the stator winding flux linkage. So let's see the flux linkage equation first, and then, okay. So now, as we know that we have currents being flowing everywhere in stator A phase, stator B phase, stator C phase, rotor A phase, rotor B phase, and rotor C phase. These are induced, of course, but these are supplied. So there is a difference. But these are currents. They have their magnetic field. Okay, once the coils get the currents flown through them, they will actually give you some magnetic flux. And once there is magnetic flux, there would be flux linkage, lambda. No question about that. So in total, there would be 6 currents, IA, IB, IC in the stator, and I cap A, I cap B, and I cap C in the rotor. So 6 currents, 3 flux linkages, because this is a stator winding flux linkage, 3 flux linkages in the stator winding. So how they would be related? So let's start. So lambda A, IA. So this LAA is the inductance by which lambda A is getting a fraction of its value for IA. LAB, so LA is this self-inductance for coil A in the stator, self-inductance for coil A in the stator. Remember, there is uniformity in air gap, uniformity in the air gap. Okay, so there is no, like the synchronous machine, In the synchronous machine, we talked about permeance. Okay, permeance along the D axis, permeance along the Q axis, air gap, reluctance, those were different. In this case, this is cylindrical rotor. So we are not bringing, you don't see any permeance effect, variation in the permeance in these inductances. Okay, only the mutual values, some constant values will be there. So there is no variation in the permeance due to the movement of the rotor. So LA is the self inductance, that is between A, stator coil A, and stator coil A flux linkage, and stator current flow through coil A. LAB, it is between this flux linkage lambda A and current flowing through stator coil B, and actually they are identical. They are identical. So these inductances, that means if you look from coil A, this is coil A, let's say this is B and this is C. So A to B mutual inductance and B to C mutual inductance and A to C mutual inductance are exactly same. So everywhere you will see LAB only, and that is actually assumed. So LAB equals LAC equals LBC equals to LAB. So this is the assumption that is being taken here. So everywhere other than the diagonal entries in this matrix, everywhere you will see LAB. Okay, that means this assumption is being taken here. So LAB is LAC is LBC, and that is exactly same LAB. And again, L for lambda B, the self inductance is the same as LAA, and lambda C, the self inductance is same as LAA. So the another assumption is LAA equals LBB equals LCC equals LAA. So this is the next assumption. These two assumptions are actually applied here. So this is your big capital LSS, you can say. L stator to stator inductance, comprised of the self inductance between the stator coils and the mutual inductance between the stator coils. So this is LSS. Let's go to the next part. So this will be between stator and rotor now. So this would be between the stator flux linkage due to the current flow in the rotor A coil, rotor B coil, and rotor C coil. Let's look at the entries now. Let's look at the entries. So the first entry, that is relating lambda small a and I capital A, means what? Means we are looking at the flux linkage of stator coil A due to the current flow in the rotor coil A. And that is how much? LAA cosine theta. So let's go back to the diagram and try to get the idea how that is being obtained. So what's the relation we are looking for? We're looking for something along this axis. So looking for the magnetic field along flux linkage along this A axis due to the current flow in this axis, isn't it? So in this axis we have IA, I capital A, and along these axes I am looking for lambda A. So what's the relation? Cosine theta. Get the idea? They have a phase difference of theta. And you take this component, you get cosine theta component. Okay. So LA is the magnitude and the corresponding angle is cosine theta. Okay, let me draw the diagram here. So that would be better in short. Let me draw the diagram in short. So this is your A axis, small a axis. This is your capital A axis. The angle is theta. So if this is capital A axis, then somewhere here would be capital B axis. And somewhere here would be capital C axis. Okay. So this was theta. Now lambda A and IB. So IB is flowing along this axis. I'm looking for lambda A along this axis. What is the relation? How much is this? And how much is this? Remember, these are rotor coils. A axis, B axis.
120 minus theta.
Yes. Which one is 120 minus theta? This
Uh,
much. How much is
yeah.
this? A axis and B axis for the rotor.
120, sir.
120. Excellent. So if the current is flowing along this axis, I'm looking for the linkage along this axis. So how much is this angle? 120 degree plus theta. Get it? And cosine 120 degree plus theta. IC, how much is this? 240 degree. Okay, 120 plus 120 plus theta. So you can either write it like theta plus 240 or theta minus 120. Okay, because this is another jump, 120 degree. Got it? Any question? No question. Now I think you can fill up the remaining blank spaces for lambda b. This part is actually the same, lambda b and a, it is LAB. Between b and b, it is LAA, because it is LAA equals to LBB equals to LCC. So this part, there's no magic, pretty straightforward. Now come to this, lambda b and IA. Means what? Means we are no more interested here. No more interested here. Theta is there. But now we are interested in B axis. So stator B axis. So this is A axis. So that means theta. This would be another theta, because this is A axis, B axis. So this is A axis. This should be small b axis. Okay. Now, so we are looking for lambda b flux linkage along this axis. So this is my axis of lambda b that I am interested on. And I want to establish the relation between lambda b and IA. Where is IA? There is IA. So how much is this? This is IA, and this is lambda b. This is theta. This is 120. So this is theta. So how much is this?
$120 minus
120 minus theta. So you get it here. Okay. Lambda b and IB is similar to this, cosine theta. So lambda b and IB. Lambda b, this is IB. So this is theta. So this is cosine theta. Lambda b and IC means what? Means the current is here, I capital C, rotor current. You are looking for lambda b along this axis. This is lambda b axis. So how much it would be? So this is 120 degree and this is theta. So 120 degree plus theta. So this is 120 degree plus theta. So in the same manner, I hope you can complete this matrix. So this is your, sorry, this is your capital L stator to rotor, LSR. This is LSS. So you can simply write LABC equals LSS IABC plus LSR IABC. Okay. And before ending, if I just try to finish the next slide, because that is identical to this one. Now the roles will be actually interchanged, because now we are looking for the rotor winding flux linkage. So the same sort of calculation, same sort of observation can be made. Simply the positions of the matrices would be simply interchanged. For example, now this is lambda capital ABC. That would be equal to, now because this is R, rotor, this is stator current. So first it would be LRS, I small ABC. This is rotor. So that is between rotor and rotor. So this is LRR. So that's it. And because this is LRS, would be exactly same as LSR. Exactly same as LSR. So you can simply copy that That means what? That means if you are standing on rotor and looking into the stator, whatever inductance you will get, if you interchange your position, means now you are standing in the stator looking at the rotor, the same inductance you will get. Mirror image. Okay, mirror image, because of the dimension, there will be no transposing even. So exactly same thing you will get for LSR and LRS. And for LRR, like the LSS, identical to LSS, here we will get LAA between lambda capital A and I capital A, and others are exactly same. All the off diagonal elements are assumed to be same. All the diagonal elements are assumed to be same. So ultimately, you will get the shorthand notation like this. Lambda capital ABC is L rotor to stator into I stator plus L rotor to rotor into I rotor. So here we will stop today because our time is up, and inshallah we will continue with our lecture in the next class from the parts transformation. Any question? Probably you can expect another assignment before your final. What about assignment 2? Already done? Assignment 2?
No, sir.
No, sir. Why, sir? Any problem in understanding, or you are not getting enough time? So these are the only two causes that you might experience. One is the lack of understanding. Okay, there could be a third option, lack of interest. Okay, so either lack of interest or lack of understanding or lack of time. So I don't know which one is true for which of you, but I hope before assignment 3 you should submit it. I will try to post assignment 3 in the next class. Okay, before Friday, on at least by this weekend. Within this weekend, I will post assignment 3. You have only 1 week left. So I would expect that you finish all your assignments before the final exam. Okay. So there will be 3 assignments for your evaluation, the replacement for the quiz, and you will have the mid exam and the final exam and the attendance. So probably this would be the distribution for your evaluation for this course. Okay. So if you don't have any question, then I will quit here.
Sir, won't we have Viva after final?
Okay. So thanks for reminding. There will be a Viva. There will be a Viva. Okay. But don't worry, Viva won't be very critical. If you understand, then you should be able to answer. No need to worry about Viva. Okay. So if you,
sir, is the second assignment deadline up to the final exam, or is it till Friday, sir?
I hope that you finish it before this weekend at least, not the Friday. Okay, let's take it up to Saturday. Okay.
Okay,
let's make it up to this Saturday. And after that, if you submit, then I will assume it to be late submission. And once you delay with your submission, you are going to be penalized. Okay. So this is the straightforward marking system. Okay. There is no non-linearity, all linear things. Okay, anything else? So because you have only 1 week left, I don't know how far I can go with the modeling. There are actually many things that could be covered, but unfortunately we don't have enough time. And also I missed probably few classes. One class I missed due to my bad health. Severe headache was there. Another class was missed probably due to a conflict with the meeting, departmental meeting. So probably 2 classes I missed, which was beyond my control. Okay, no question, then I think we can stop here and see you inshallah in the next class. Assalamu alaikum.